Okay, so we're back. I am recording, and I think you all should have got a permission to let me record because I'm going to be posting these. So if you want to watch it later, that you'll be able to. Okay. Yeah, so we're going to talk about computational intelligence. Let me tell you a little bit about the history, and we're going to go through the history of computational intelligence and why this is a class in computational intelligence as opposed to artificial intelligence. One of the things that we are not going to do is get a lot of software experience. If you want software experience, there are other classes which you should take. One is offered by Professor Dong. And that's what he does. He goes in and he uses all of the software that's available, and you have assignments, and you can look at those assignments and do great and wonderful things by playing around with the software. The name computational intelligence actually came up in the late 1980s or early 1990s because there was a big fight, and we'll talk about this fight between so called connectionists and those that do expert systems. Now, expert systems are where you talk to a person, maybe a doctor, for example, and you say, if this is a symptom and this is a symptom and this is a symptom, then your diagnosis is this. And you would enter that into the computer. And after you entered it into the computer, um, I'm sorry, it just occurred to me. My trains of thought are not having a caboose. So excuse these little spurs. I think that when I record this, um, that Akram, you're going to be on the video. You're going to be on the recorded video because I'm seeing you. No, and it's not your fault. It's not your fault. I don't know what to do. Oh, pin. Okay, pin. There it is. So if you right click on me and you go to pin, you can pin me. And when you pin me, that's all you see. And for this class, that's all you need. I'm all you need. Um, Okay, so good. I think I have that worked out. So again, a right click and a pin. A right click on my little picture and then pin, and you will see me. Okay, my name is Robert Marks. I spent a number of years at the University of Washington in Seattle, where I became a full professor, did lots of research in AI, mostly with a guy named Les Atlas and also another guy named Mohammed El Shikari, who and both very, very good friends. And we did a lot of applications. Now, I don't know if you know this, but engineers come in two sorts of colors. I shouldn't say colors. Maybe that isn't culturally appropriate. Two different types, if you will. I think that there are engineers with solutions looking for problems and those with problems looking for solutions. Now, the guys that I work with, Les Atlas, he had lots of problems and he was looking for solutions. And I'm good in algorithms and things such as AI. So I'm the type of engineer that have solutions looking for problems. I think that most of computer science are people with solutions looking for problems. And you could go in and you can do that thing. So that was true with all of my collaborations, and they've been very fruitful. If you have somebody with problems and you have a package of solutions, you could go in and really help them. So Les Atlas was very interested in speech recognition. So we did a lot of early work in speech recognition, and were able to do some very interesting things, and actually contributed, as we'll see, to convolutional neural networks. And then the work with Mohammed El-Shikari was power load forecasting. In fact, two of the big successes of early AI in the 90s, in the 1990s, was application of neural networks to forecast power loads for power companies. And we got into a contract with Puget Power, and we started looking at their data, and we're actually able to um, we were able to forecast their power loads better than they were able to before. And in about a year and a half, there were 32 different companies, power companies, using AI in order to forecast their load. Um, oh, I just noticed something. My goodness. There's such a glare off my head. I think if I had a makeup artist, they would come in and put powder on it. Isn't that the way you get rid of the reflections? I'm not sure. Okay. Well, you're going to have to live with it. Just think of it as a halo or something. Okay. Yeah. So that was the early days. Now, let me explain to you the war that was going on at the time. There were people such as Marvin Minsky and Seymour Papert, who were at MIT, And they did not like neural networks. They called it connectionist. And they were the people that liked to do expert systems, which is you look at a set of rules and then you write those rules into computer code. And they did not like connectionists. So, therefore, at the time, the word artificial intelligence was associated totally with the expert systems. And it turns out that the connectionists, that is, the people in neural networks, wanted to distance themselves from this. So there was a guy named Jim Bezdek who suggested the name computational intelligence. And computational intelligence at the time was different than artificial intelligence. Currently, today, of course, they're both fused into the same thing. In fact, the two have fused. If you look at large language models right now, you have a lot of experts digging around and putting band-aids on large language models that don't work. So you do have this human expertise which goes into the software. So it's kind of hybrid now. But back then it was a big deal. There is a society now in IEEE called the IEEE Computational Intelligence Society, and they're primarily connectionists. And computational intelligence encompasses more than just neural networks. We're going to talk about so-called fuzzy systems. Fuzzy systems, you probably have used appliances today that have underlying software based on fuzzy systems. The Japanese actually pioneered that. So we're going to talk about fuzzy systems and the beautiful math behind fuzzy systems. And people hear fuzzy systems and they think, oh my goodness, that sounds kind of wonky, fuzzy. That's a terrible word. But the guy that coined it was Lotfi Zada. I think he was from Berkeley. And he said, no, he liked the term fuzzy systems, but it kind of screwed things up. When I was at the University of Washington, I I work with Boeing because Boeing used to have a big presence there. And we worked on a fuzzy system for automatic braking. It turns out that the Boeing planes had very mechanistic braking. So when a plane came in to land, you had this automatic braking system, and well, this part didn't work, so they added a little bit on, and this part didn't work, so they added a little bit on, and that's referred to as mechanistic, where you put little band-aids on things. And we proposed a technique based on fuzzy systems, which gave a nice, smooth automatic landing and automatic braking. And at that time, I learned the difference between um, I learned that fuzzy was not a popular term. I also found out the name for the first derivative of acceleration. The distance is a function of time. If you take that's derivative, you get velocity. If you take the derivative of that, you get acceleration. Do you know what you'd get if you get the derivative of acceleration? Jerk. And when your plane lands, if you notice, there's a change in acceleration. So you go back in your seat and there's a jerk that happens. And then you know what the derivative of jerk is? Snap. And the derivative of that is crackle, and then there's pop. Seriously, look it up. Ask ChatGPT. So anyway, I looked at that, but we proposed this to the Boeing brass. We said this is really great, but they totally turned it down. Their main reason was, he said we can't ask people to fly in an airplane that is controlled by fuzzy logic. So therefore, that was a bad term that and kind of screwed up our research effort, even though that the tests that we did on the automatic testing systems they had there was a lot better. So we're going to learn about fuzzy logic. We're going to learn about swarm intelligence also. Swarm intelligence is different than AI that you're used to. And swarm intelligence is based on a number of things. I think most fundamentally, we're going to look at swarm intelligence based on the way that insects and birds and fish do their self-organizing. If you ever think about it, how can dumb bugs like ants build these beautiful colonies? Or how can termites build these beautiful architectures underground with all these tunnels and things of that sort? Well, it turns out it's swarm intelligence. And the bugs are pretty dumb. They don't know what they do. So they follow simple rules. But those simple rules are put there by God in order to give them an emergent property. So we'll study swarm intelligence also. So swarm intelligence, and then we'll study evolutionary computing, Evolutionary computing is one of the areas of the Computational Intelligence Society. When I was involved extensively, I used to be involved a lot in the politics of that society. I was the president for a while. When I was involved, there were three main areas. There was the neural networks, there was the fuzzy logic, and there is an IEEE transactions on fuzzy systems. And the other one is evolutionary computing. And there is a journal called the IEEE Transactions on Evolutionary Computing. So those are the areas that we're going to look at. Then we are going to look at why these different neural networks work. It turns out that everything you see is uses as a tool error back propagation. And so if you're familiar with large language models or GANs, generative adversarial networks, or even the process of diffusion, which is a way to generate deep fakes, you're probably familiar with error back propagation. That's what they use in order to train these things. And so I refer to these things collectively, and that includes like large language models, GANs, neural networks, deep learning, all of that as backpropagation sort of systems, because that's the fundamental core that exists in them all. So we'll go over error backpropagation, and we will actually have a discussion. I'm going to ask you to listen to a podcast with Paul Werbos, who was the guy in 1975 that actually discovered error backpropagation in his Harvard PhD dissertation. And you talk about something that has really revolutionized things. I, I do the interview with Paul Werbos, and I ask him. I told him. I said I think that error backpropagation is probably on the top 5 or 10 most commonly used algorithms in the world. I think probably number one is the cosine transform, which is used to make JPEG images. And then down the list is probably the fast Fourier transform. But error backpropagation is used extensively on all of the early neural networks we'll use. So we'll look at error backpropagation and look at how people have formed different architectures in order to generate these different beautiful artificial neural networks, including the large language models like ChatGPT and Grok, and also GANs, which are fundamental to deep fakes. It's just beautiful the way that they've used this single tool. And it's kind of like Legos. You put them together in different ways and they do different things, but you have to be very clever in how you put them together. So we will talk about that. So those are the things that we're going to be covering in class. So again, this is not going to be deep into the use of AI. It's going to be more an overview of AI, getting into the specifics, getting into the mathematics. I enjoy the mathematics. I almost was a mathematician in my younger days, but I found out that mathematicians don't make a lot of money. Engineers do. And in fact, I'm friends with the new chairman of the mathematics department here at Baylor University. His name is John Davis. And he's told me a bunch of jokes. The most famous is the best one is, what is the difference between a bachelor's degree in mathematics and a large pizza? And the answer is, you can feed a family of 4 with a large pizza. But it's difficult to feed a family of 4 with a degree in mathematics. And it turns out that most of the mathematicians go into applications, applied fields, and things of that sort. But I'm getting a little bit off base. Okay, there is a so let me go ahead and do the best I can here in the time that we have left. It turns out that there's a lot of hype concerning artificial intelligence. This has been around for a long time, and we'll talk about it. Where did artificial intelligence come from? It actually started in a 1956 summer Dartmouth conference. And here they had a lot of people that were very instrumental in founding artificial intelligence. Okay, hopefully you can see my cursor. Back here is Marvin Minsky. He was the one that liked expert systems. We have here Ray Solomonoff. Ray Solomonoff was instrumental in one of the 3 founders of algorithmic information theory. And over here to the right is a guy that really needs no introduction, which is Claude Shannon. Now, Claude Shannon in 1948 wrote a paper for Bell Labs in which he talked about the information theory. And it was just a beautiful paper. In fact, when I teach the graduate course on information theory, we basically go through his original paper because it was so complete. It was really incredible. Up in the upper right is a guy named John McCarthy. Now, John McCarthy formed this 1956 Dartmouth Conference, and he coined the term artificial intelligence. So if you want to talk about who's to blame for the word artificial intelligence, I know a lot of people don't like the term artificial intelligence, but it is actually this guy in the upper right. A lot of people say that artificial intelligence really isn't intelligence at all. I don't know. We're not going to argue about that, I don't think. Now, it turns out I'm going to present kind of a quick history of artificial intelligence. And we're going to be talking about the landmarks. And we're going to go through each of these steps to show that the development of artificial intelligence, and I'm specifically talking about here in neural networks, that the perception was a number of breakthrough papers. Now, a lot of people believe that AI is going to take over and write better AI. We're going to give arguments against that and why that can't happen. And I think that this list is evidence that indeed that doesn't happen. We have a number of things dating back to 1943, the McCullough-Pitts neuron, all the way up to 2017, the transformer models, which are used for large language models. And each of those is due to the ingenuity of of human beings. None of these steps was generated by artificial intelligence. It was all by human ingenuity. In fact, we'll talk about AI writing better AI when we get to a topic called model collapse. And it really suggests that AI is not going to write better AI. And there's other reasons for that. In order for AI to write better AI, it has to be creative. You have to create something. And we'll talk about a definition of creativity and argue that AI, in fact, computers themselves have never been creative. So these are the different steps. So let's go through them one at a time. 1943, the McCullough-Pitts neuron. It was the first mathematical model of the neuron. Nobody had done this previously. It's a simple binary threshold, and what it is you have a number of weights here. And again, I hope you can see my cursor. You have a weight here and a weight here and a weight here, and then you have these inputs. These inputs are multiplied by the weights, and they are added up. So again, the inputs, and where do these inputs come from? They can come from, well, at least in this first model, it came from like sensory things. So it would be like from the eyeball or the nose or something like that. And you add this up, and this is the nose neuron. You add all of these up, you submit it to a summation, and then you present it to a threshold, and the output is either a 0 or a 1. So in terms of math, the output is equal to h. Now, h is referred to as the Heaviside step function. Nobody's ever heard of Heaviside. Anybody heard of Heaviside? Okay, what's Heaviside, Riley?
Heavy side was brought up in RF1 in the beginning of getting microwave circuits introduced commercially. That's as much as I know, but I've
Okay,
heard the name.
he was astonishing. He used mathematics, which wasn't rigorous, and Riley's totally right. But he used mathematics, which was not rigorous. Instead of using derivatives, he used a symbol like S. And so he actually was kind of a pioneer of use of things like Laplace transforms. Um, y'all are familiar with Maxwell's equations. And there's four Maxwell's equations. And everybody thinks that Maxwell came up with this. They didn't. Maxwell came up with a lot of different equations. It was Heaviside that actually concatenated all of Maxwell's work and came up with the four steps of Maxwell's equations. So he's an unheralded person. And the only thing that historically is named after him is the Heaviside step function, which is one for above a certain threshold and 0 for another threshold. So good for him. We got Heaviside living on in terms of terminology. So you know you made it if you have something named after you. And and therefore this was the first model from McCullough and Pitts in 1943. And you had these different connections. And in modern neural networks, it turns out that these X's come from different neurons. So you have neurons connected to neurons. And so these if the other ones are McCullough-Pitts neurons, this one is either turned off or on, 0 or 1. This one's turned off or on, 0 or 1. And so you have a bunch of these and they go together. But McCullough-Pitts didn't develop this in much beyond this. So it turned out that in 1949, Hebb came up with Hebb's law, which is neurons that fire together wire together. And he said, okay, if we have a couple of neurons, here's a neuron up here, here's a neuron down here. Now, neurons fire or they don't fire. They generate an output or they don't generate an output, at least in a rudimentary sort of way. It turns out that there's a weight corresponding to the connection between the two neurons. This weight changes when both neurons are firing. And so when both neurons are firing, there is an increase in the weight between the neurons. And this has been reduced to the phrase neurons that fire together wire together. And so that is Hebb's law, 1949. Synapse strength when a presynaptic neuron repeatedly and persistently helps trigger a postsynaptic neuron. Presynaptic is kind of an input, the other one is the output. And again, cells that fire together wire together. So that was his law. And then engineers got a hold of this. I think that most things in engineering are found through nature, and we were inspired by neural networks by the piece of meat between our two ears, by the brain and the neurons. And so these were biological sort of things. And so we had to have somebody that came along and tried to apply this to neurons. And this was first done in 1958 with Rosenblatt. Rosenblatt was a professor at Cornell. He did a Rosenblatt perceptron. And what he did is he took the McCullough-Pitts algorithm and he applied it to actually doing some certain problems. And it worked okay. And he also did something else. When it made a mistake, it nudges the weights. So, for example, if the output is wrong, then you adjust the weights to make it closer to being correct. It's kind of like Pavlovian learning, if you will. If you want to teach your dog how to get yourself a pack of potato chips, you say, go get something. And if he brings you a pack of Cheetos, you take a newspaper and whack him on the ear and say, bad boy. And then he goes, gets you I don't know, some little weenie dogs. And you say, nope, bad dog. And you whack him on the ear. So his brain is being wired through this idea of through reinforcement learning in order to respond properly to what you want. And eventually he brings you the pack of potato chips and you say, good dog, good dog. And you know then that you've trained the dog. And that's the way that Rosenblatt's perceptron worked. And it worked pretty good, but it had a lot of limitations. We'll talk about those limitations a little bit. And notice this was in 1958. A lot of people think that AI is something new, and it's been around for a long time. And what has made it great is increase in computer power. A lot of the algorithms that we're using today have been known for quite some time. We just haven't had the computational power to look at them from a strong perspective. So this is a guy that's kind of one of my heroes. He's the one that I'm going to ask you to watch the video about. This is Bernie Woodrow. He was at Stanford, and he's the one that used the adaptive linear neuron. And he said, he called it Adeline. That's a contraction of adaptive linear network. And he appeared on this TV show called Science in Action. I believe it was in 1961. And he overwent all of the different ways that he could use his Adeline. And I've mentioned these already. There are things such as playing blackjack to a championship level, forecasting the weather better than the local forecaster, doing rudimentary speech prediction. We can do it a lot better today, but he was able to actually take a spoken voice and have it type out what the voice was saying. And this was frankly astonishing for the 1960s. And it was the same as the perceptron, except the difference is these states were no longer ones and zeros. He let them be floating point numbers. And by letting them be floating point numbers, he was able to get greater generalization. And he used it and he trained it with something called the Woodrow-Hoff algorithm. Hoff was one of his graduate students. And you know you've made it if you're a graduate student and you come up with an algorithm that's named after you for the rest of your life. We're gonna have some of those when we talk about information theory, where the breakthroughs came from the graduate students. And breakthroughs do come from the graduate students. They come from people your age. And when you get old like me, your mind is kind of in a rut. You've learned things and you think there's things impossible to do. You're not smart enough to know that there's things impossible to do. So if you look at people like Einstein, Einstein was in his 20s when he came up with relativity and worked at the patent office. Um, Newton was in his 20s. Kurt Gödel, who toppled an area of mathematics, was actually in his 20s when he came up with his incompleteness theorem, which people are still studying and trying to understand today. So it's the youth that make all of these great things. So be creative and hopefully continue that legacy of coming up with creative things while you're still young and you don't get calcitrant. Um, I like to illustrate this, and if you get the answer to this, I want you to raise your hand. Isn't there a hand raising thing here somewhere? Is it under chat? Okay, no, it isn't under chat. Okay, let's just do this. Um, there was a little Russian boy. He was in his car, and he was driving along, and the Russian guy came on. The kid knew nothing about U.S. history. And the guy said, "You know what? This is really interesting. The United States is a bad country," because this was Russia, of course. He says, "But they have some remarkable things. They declared independence on July 4th, 1776." And here's something which is interesting. The first five presidents were Washington, Adams, Jefferson, Madison, Monroe. He said, this is astonishing if you think about it. Three of these presidents died on July 4th. And it's true, three of them died on July 4th. So the question is, can you figure out why or which one of the presidents died on July 4th? Um, and it's not a probability of 3 out of 4, it's with total certainty. Anybody have an idea of how this little boy knew with certainty that it's true? Okay. Riley, you've heard of this already, haven't you? Okay. So if you've heard about it, you're not allowed to play the game. But if you haven't heard about it, anybody want to give it a try? Go ahead and unmute yourself and chime in. And then I'll tell you what you're trying to do, what I'm trying to do. Okay. Nobody knows. Well, this shows that your mind is in a rut. And it gets deeper into a rut as you get older and you can't see out the edges. The idea was not in probability, and we're all engineers, we're all nerds, and we think in terms of probability. But this guy thought in terms of psychology. Anybody else except Riley know the solution to this? Okay, Riley, since you're the only one, I'm going to let you tell. I'm going to let you tell the answer. Go ahead.
So if I remember correctly, the answer is the first three presidents were the ones that died on July 4th.
The which one
Uh,
now?
the first three.
Okay, that's
Um,
wrong.
the,
You're wrong. Oh, good. Okay.
okay.
Why do you say the first three? What's your reasoning?
My reasoning is that if it was the first four, then we would say four of our
Oh,
presidents
okay.
have died.
You're very close. And the answer is in psychology. But here's the proper answer. Um, there was Washington, Adams, Jefferson, Madison, Monroe. And the guy said, "This is astonishing." He says, three of these died on July 4th. Well, it has to be the last one, Monroe. If it wasn't Monroe, if it was one of the other four, he would have said, this is astonishing because of the first four presidents. He would have made it even more astonishing, right? So the answer is in the psychology of the question as opposed to the probability, and I think that illustrates that that your mind is in a rut. I once was in Japan on a mission trip, and I was with a guy that was with Campus Crusade, and I gave him this riddle. He said, "Well, of course, it's the fifth one." And he had no background in technology at all. His mind was not in a rut. So that's kind of interesting. So for that reason, do great things while you're young and your mind is not doesn't get any deeper in the rut. Okay. So I one of your homework assignments is to watch this video. The link is on the Google Sheets page, and you can take a look at that there. Now, it turns out that neural networks were really a big thing at this time, and there was still this fight. There was this fight between the people that wanted to do expert systems. They wanted to do things by rules. The connectionists wanted to do things by example and train neural networks and things of that sort. And there was this incredible fight. And the person that really liked the idea um, of expert systems was Marvin Minsky. He, by the way, went on to find the MIT Artificial Intelligence Lab at MIT. He's a smart guy, okay? But he didn't like the idea. And so what he did is he took a colleague called um, Seymour Papert, and here they are. This is Minsky and Papert. They were both at MIT, and they wrote a book called Perceptrons. Perceptrons just spent the whole book criticizing neural networks. They criticized this, they criticized that. Even as he got older, Marvin Minsky still didn't like Marvin Minsky still didn't like artificial intelligence, even as he got older. In fact, there's a video that he says, "You know what? Artificial intelligence will never figure out how many objects there are in a picture. So if you have four apples in a picture, it will never be able to count them," according to Minsky. Now, I tested this out because it turns out to be in ChatGPT that in ChatGPT, you can sometimes log on and they do a test whether you're human or not. And they show objects and they show an object and they say, pick the picture where there's three objects in it. Has anybody done this? And then you scroll, the first one has, say it's a pumpkin. So you do with one and there's two pumpkins. And then you go to the next one and there's four pumpkins. And you're looking for three pumpkins. You go to the next one, there are three pumpkins. And so you say, yep, this is the right one. And you have to go, excuse me, you have to go through a number of those tests. And has anybody ever gone through that test at all? Okay, so you have gone through that test. Julius Markle has done that, and so what I did is this is good for ChatGPT. So I did a screen capture of all of these different articles, and I asked ChatGPT to choose which one had three pumpkins in it. And of course, the objects change from test to test. So I did it over and over and over again. ChatGPT never got it. So at least from ChatGPT, I think this is ChatGPT 4, at least from the perspective of ChatGPT, Minsky is right. Artificial intelligence can still not count the number of objects which are in a picture. I thought that was interesting. Now, does this mean that AI can't? Yeah, it can, but you have to do some image processing on it. You have to do image recognition and partition and things of that sort, and then maybe use some artificial intelligence. But there's a lot of front end stuff that you have to do it. But just giving it raw to ChatGPT, it didn't work. Maybe they've figured that out, but according to Minsky, he says that will never happen with artificial intelligence. By the way, I doubt that that's true. I would imagine that you can indeed do that. So anyway, they wrote this book, and it turns out that at the time there was all this funding for artificial intelligence. It came from DARPA. In the Great Britain, there was a lot of funding on artificial intelligence. And as soon as this book was written called Perceptrons, which was the name of Frank Rosenblatt's artificial intelligence, as soon as that happened, um, all of the funding dried up. And Minsky and Papert shot themselves in the foot because it turns out all the neural network stuff dried up, but so did all the artificial intelligence, all of the expert system funding went away. And so I still meet a lot of older people that remember this era. And they said, nah, neural networks kind of stink. Now, I haven't met anybody in maybe 10 years that was about this, but there's a lot of people that still remember this era, and they think that indeed this should be that this should that neural networks still kind of suck. Okay, another breakthrough in artificial intelligence was 1975. This is back propagation introduced by Paul Werbos. And again, error backpropagation, sometimes just called backprop, is the core learning algorithm used to train multi-layer artificial neural networks. Now, it turned out both the Adeline and the Rosenblatt perceptron just had an input layer and an output layer. It was kind of like your senses, and then what do you see? Okay, so you put in a picture of an apple, and it says this is an apple, and there was just one layer. What Werbos's backpropagation allowed you to do is put in so-called hidden layers. So you put in these layers and between the input and the output, and that increased the generalization of the neural network incredibly. But here's the question: how do you apply Hebb's law to this? If you have a couple of neurons that are in the hidden layer and they are, um, and how do you apply Hebb's law? When they fire together, they're wired together? I don't know. Each of these weights, for example, the W's, is what you need to find out. And so you see the weight W11, W21. When you train a neural network, what you're trying to do is you try to find all these weights in order to match the input to the output. And so that's what it's trying to do. So we have an input layer, a hidden layer, and an output layer. And I did an interview with Paul and I want you to listen to it. It's only about 30 minutes. And he talks about his discovery of error backpropagation. And he was a young guy, just like Newton and Euler and all of these other people that were doing great things when he was young. Anyway, after the Perceptron book, there was this AI winter where there was nothing happening in artificial intelligence until people recognized Paul Werbos's contribution. Now, Werbos made the contribution, but he wasn't the one that exploited it. I don't know if you know this, but you know the Nobel Prize last year was won um, by two guys in neural networks.
Hinton.
Yeah, Hinton and Hopfield.
Oh yeah.
Now, in my opinion, and I wrote an article about this because it kind of irritated me, neither of these guys deserve the Nobel Prize. In my book, Non-Computable You, I go through the history, much like I'm going through right now. And the title of my Hopfield chapter was Hopfield's Neural Network of Little Use. Nobody that I know of right now uses Hopfield's original neural network to do things. They use similar things in neuromorphic systems, but Hopfield's original neural network was just terrible. It scaled terribly. If you increase the number of objects you were trying to if you increase the number of neurons, the number of interconnects went up as the square, so it didn't scale well. The storage capacity, there was a diminishing returns as you got larger and larger, and it was not a very good algorithm. But nevertheless, he won the Nobel Prize. John Hopfield of Cornell University. The other one is Jeff Hinton, and I have no idea why Jeff Hinton won the Nobel Prize. Uh, he didn't do any of the landmark papers. He was recognized as one of the people that popularized the idea of convolutional neural networks. He doesn't have a very good record of forecasting. I think it was 2000, I don't know, in the mid 2000 teens. He predicted that because of convolutional neural networks, all of the radiologists in the world would be out of work in 5 or 10 years. Well, it turns out that 5 and 10 years have passed since his prediction, and it isn't true. It turns out the convolutional neural networks, which recognize things like tumors and such, they're really good, but they're still used as tools, and there's actually a shortage of radiologists now. And he's also the one that has predicted, if you read some of his forecasts, that in the future, he's all concerned about neural networks. They're the biggest existential threat in the world, and I think that that's baloney. I think it was Ralph Nader. He wrote a book called "Safe at Any Speed." This is a while back, and what he was trying to do was he was trying to show that there was a car, and I forget the name of the car, but it was very dangerous. He said this was the most dangerous car in the world, And he gave all of the stats. They had the fuel tank in the back, so if there was a rear end, it exploded and stuff like that. So it was a very poor design. But a reporter asked him, okay, well, what's the second most dangerous car in the world? He had no idea. He was using this as hyperbole in order to make a point. This is what Hinton is doing with the neural network. He's saying that neural network is the biggest existential threat. I don't think it is. I think the thermonuclear weapons is the biggest existential threat. And I think it's a lot more threatening than artificial neural networks. So Hinton and Hopfield won the Nobel Prize. I wrote an article and I said it should have been Bernie Woodrow and his pioneering work in the 60s and Paul Werbos, who discovered error backpropagation, which is one of the most used algorithms in the world, should have won the Nobel Prize. And so I'm a little irritated at the Nobel Prize Committee who gave Barack Obama the Nobel Prize in Peace 9 months after he was elected president, even though he had done nothing for peace. And since, by the way, the Nobel Committee has apologized for that Nobel Prize, so good for them. At least they're true. So error propagation, it turns out, addressed a lot of the problems that were put forward in the book Perceptrons. Um, in the book Perceptrons, one of the big objections, and we'll go through this, one of the big objections was that you could not, you could only classify things which were linearly separable in some sort of feature space. And he said that was too limiting. Well, it turns out with error backpropagation, you didn't have to have this linear separation. You could do great and wonderful things with it. So it addressed a lot of the problems that Minsky and Peppard had. I notice I've gone over a little bit and I don't want to go over. So I think that we'll go ahead and end it right now. And we'll take this up a week from today. Again, a week from Thursday is class off. And I want you to listen to the Bernie Woodrow interview in the 1960s and see how this history in some way has been lost. He just did astonishing sort of things. And also the interview with Paul Werbos and his flash of genius, how he got the idea for error backpropagation. Okay, so until next time, be of good cheer. We'll see you all.